And for this panel, I have the honor to have our colleagues from University of Texas, Washington, and Michigan, and to have Maryann moderate the session on making human data discoverable. So Maryann, thanks for taking the task.
Okay. Thank you, Lucilla, and thank you all for your attention. So the title of this particular panel is Making Human Data Discoverable. I don't know if I'm the only person in the room who actually doesn't deal with human data at all. But in the context of a project that you're going to hear about soon and was mentioned already by Kari, basically how do we make data discoverable in general, and what are some of the issues that are specifically involved with human data is something that we're going to be thinking a lot about in the course of the next few years. So I'll talk a little bit about, just by way of introduction, the work that I do in a project called the Neuroscience Information Framework. But whenever we talk about making data discoverable in our domain, which is in basic research, everyone's like, oh yeah, well, we've got Google. What's the problem? You know, because basically we all have to remember now that no matter how great our resource is and how great our database is and how easy it is to use a structured interface to find what you need once you know the database is out there, most people when they're starting are going to start with some sort of web search. They're going to go to a web and they're going to say, okay, what sorts of things do you have available to me? And as those of you who work in database know, the web was not really designed for data. It was designed for documents, and that much of what is contained in the databases, never mind the special access privileges and everything else you need to know for protected data, is already itself not particularly web accessible. So you cannot search the dynamic content of databases particularly well through a search engine. Google's working on it, lots of people are working on it, but it still is very difficult. And just to give a notion of the scope of the problem, this project that I mentioned, the Neuroscience Information Framework, and also its sister project, DKNet, for metabolic disease, has been cataloging research databases for the last 6 years or so. So we go around, the nucleic acid research issue is very good, but we go around the world and we try to figure out how many databases and other sorts of research resources are available out there for researchers to use. And you can see that there's quite a few of these, and those of you who can't read the number, I've put it out here, that there's over 3,000 of these databases and data sets that are scattered around. Now that's not just human, but if you just restrict it to human, you come up still with around 1,000 or so, and that doesn't include the biospecimen repositories and everything else. So it just tells you that if your data is scattered throughout all of those, how would you even know? If one of them there is going to be able to answer your question, how would you know even to go there to begin to pose your question? So I'm not saying that we have the answers here. Hopefully within a few years we will. But we certainly know that requirements for effective data sharing, we've talked a lot about them today, of all the things that we need to know. And I think one of the most important things, which I like to point out in my presentations to researchers, is that there's a duality of modern scholarship. It is not just you as a human being being able to understand, but that a machine somehow can understand it. And I think when you think about how many databases there are, the need for a machine processable and machine accessible metadata is extremely important. Being able to understand the access rights, because for those 1,000 databases, we have 1,000 free text things that tell us who's allowed to use it and when, and that's very, very difficult. So, our panelists today are George Alter from the University of Michigan, Hua Xu from the University of Texas, and Kari Stephens from the University of Washington. They're not going to necessarily address specifically the things that I mentioned, but they are going to talk about their particular systems and their experiences with making human data discoverable. So that's it for me. And George, you want to get your slides here while I introduce you? Let's see. So I'm pleased to introduce George Alter, who is the director of the Inter-University Consortium for Political and Social Research, which I know as ICPSR. And he's been doing this for a long time.
I think I'm going to need some help on this.
To get the, here's the panel right here. You are
There we go.
right there. Okay, and timer.
Thank you, Maryann, and thank you very much for including me. I've learned quite a lot today, and I'm really pleased. So I'm going to talk about two things: data discovery, and in our discussions on the panel before this, Maryann asked about what we do about sharing confidential data. So I'll talk about that as well. This is the mission statement of ICPSR. our full name is up there, Inter-University Consortium for Political and Social Research, which is why we go by the acronym. And we were founded in 1962 to share the American National Election Studies. And at the time, we were a consortium of 21 universities. Today, we have 750 member universities around the world. So this is actually very relevant to what Maryann was talking about. In order to find things in the kinds of data sets that we have, you have to know a lot about what the content is. The average data set at ICPSR has more than 400 variables. If you think about a spreadsheet, you're thinking about more than 400 columns, each of which has a different meaning. And many of our data sets have thousands and tens of thousands of variables. So this is just an example of one code book from a recent study. About a dozen years ago, ICPSR was a co-founder of the Data Documentation Initiative, which is an XML markup standard for social science microdata, and this is what it looks like. And ICPSR now uses DDI as a part of our fundamental workflow. We've got about half of our collection marked up in DDI to the variable level, and as a result of that, we have a database now of about 4 million variables that we can describe in DDI. And this is an example of one of the kinds of things that we're beginning to build for the benefit of researchers using that technology. So this is our search engine, and in that one search box there are a number of different things you can do, but if you put phrases in there separated by commas and then choose the variable relevance sort by, what you get is a display that searches within each data collection, with each data set, for all three of those variables. And then under each data set, it shows you the variables that are relevant to your search in columns by what you searched for. And each of the variables has a checkbox next to it. If you check those boxes, you get another display that shows each variable with frequencies, the question that was asked, and sometimes some other information. And you can actually go from this display to the particular data set and navigate through the code book. So increasingly what we're moving towards are two things. One is code books that are online and interactive, and also a discovery system where you're discovering not just an abstract about the study, but really very detailed information about what question was asked and what were the possible responses on that. And we're very interested in as the national infrastructure for data discovery develops, that we be able to integrate into that this detailed metadata that we're creating. So this is sort of the framework that we at least I think of when we're thinking about sharing confidential data. This actually comes from some work that was done in the UK, that there are a number of different strategies for making sharing of confidential data safe. You can try to make the data safe. You can look for safe places to share the data. You can try to make the people safer, and you can also make the output safer. So I'll just tell you a little bit about what we're doing in each of these. So there's a long history of techniques for doing data masking, and we don't do that. We do this a little bit on most data sets, and in some cases we do it a lot. Mostly what we do are the very simple things at the top. So if there's a question about income in a survey, we don't give you the exact income. We usually do what's called top coding, so people who make, I don't know, 200,000 or above, so you can't identify the really rich people in there. But this is one way of making the data safer, making it less re-identifiable. Secondly, safe places. So there are a number of different techniques that are emerged, and you heard about some of them today, some very sophisticated ones, about providing the data in a place where it can be protected. So one approach is a remote submission and execution where the work is done somewhere else. Another one is what we call a virtual data enclave. That's a remote desktop type system where the data reside in a protected data center, and users have to authenticate to get in. And for the most sensitive data, we actually have a physical enclave. That is to say, we have a room in our basement where if you want to use the data there, you have to come to our facility. We go through your pockets on the way in, we go through your pockets on the way out, and you don't get anything until we've checked it. Safe people. How do you make people safer? Well, one way you make them safer is with legal agreements, and you heard some discussion of that today. We distribute a lot of confidential data under data use agreements. One thing that I think we haven't done enough of, at least in our disciplines, and we're trying to work on, is training. We actually had a group that's worked on what is now in a PowerPoint slides, but training in disclosure risk and the things that researchers should and shouldn't do to protect the confidential data. And I think we need to do more of that. Finally, safe outputs. This is something that you get if you control the data provide the data in a controlled environment, which is that you get to check the output before you give it to the researcher. And both in our physical enclave and in the virtual enclave, the requirement is that the data stays with us, and any output someone wants is vetted before it's sent to them. This is common in a number of areas in the social sciences. As I understand the current state of this science, there are some things that can be automated, but generally we still rely on a manual review of someone who actually reads through things, which means that there's also a certain training that you have to give to your users so they know that if they're going to try to do every possible combination of crosstabs, it's going to take them a long time before they get their output. That's where I'll stop. Thank you.
Oh, then I don't have to get up. Okay. Next up is Hua Xu from the University of Texas. He's an associate professor at the School of Biomedical Informatics in the University of Texas Health Science Center at Houston.
Good afternoon, everyone. So my talk will be more focused on technical aspects about building search engines for biomedical data sets. Okay. I probably actually don't need this slide talking about importance of biomedical data reuse. So I'm going to just skip to the second slides, which I want to give you some background about the NIH Data Discovery Index grants, which Lucilla already mentioned previously. So in 2012, the Data and Informatics Working Group generated a report for NIH director, and they suggest to promote data sharing through central and federal data catalogs. So in response to that report, early this year, NIH issued an RFA called Development of an NIH BD2K Data Discovery Index Coordination Consortium. It's a U24 grant RFA. And the goal is really to build a NIH Data Discovery Index to allow discover, access, and citation of biomedical data. So the idea is simple, just like we're dealing with publications. Each publications have a PubMed ID. Then when you cite it, you can use the PubMed ID. The idea for data index is we are thinking about maybe assign a unique ID for each data set. Then we study how people cite the data. For those people generate data set, how we can give them credits. So it sounds like simple, but actually when you compare the data set versus the publications, data set is much more complicated. There's a lot of different complicating goals of different players, stakeholders involved in this data processing. So as Lucilla already mentioned, we actually proposed the BioCaddy, shortened for Biomedical and the Healthcare Data Discovery Index engine. And it is likely we will get funded for this project. So the goal is really we're trying to build a sustainable ecosystem for making biomedical data sharing by engaging a broader community of stakeholders. And focusing on three aspects: discoverability, how we can easily find the data set you want, and access. Once you find the data set, how can we help you easily download data and use the data for your own research? Then citation, how we can help people easily cite the data sets, and how we can generate like those, give the credit to people generate data set. For example, help a faculty get promotion. So there's many different issues in this proposal, and our team at UT Health actually primarily focus on technical aspects of discoverability. So we are looking to different approaches to search biomedical data sets. So there's a number of technical challenges when you're thinking about searching biomedical data sets. First of all, it's about the complexity of the biomedical data set. Thinking about the biomedical data set ranging from molecular, cellular, to all the way to the populational data. Each type of data have different characteristics. And the building, there's hundreds of different ontologies to describe all those different type of medical data. And building something with that complexity is very difficult. And the other issue is really related to our research is a lot of description for biomedical text data, biomedical data set is in narrative text. And searching those narrative texts needs additional sort of informatics approach. And my research is primarily focused on one technology called natural language processing, which also have been described in the previous presentation. So there's a different ways to building search engines for biomedical data sets. And here I just list the three different projects. The first one is the P-Finder project. It's also led by Lucilla, and I'll show you a sort of typical use of natural language processing, NLP, to standardize the representation of description of biomedical data. Then the next two projects is the two projects we're going to start by using the DDI supplement funds. One is NLP-enabled Elasticsearch approach. Another one is a semantic vector-based search, which is going to lead by Trevor Cohen, who's actually sitting there. So next a few slides, I'll describe a little bit about the P-Finder projects. It's a shortened for phenotype finding in data repository. The goal of P-Finder project is to improve the search of dbGaP. I guess everyone knows it. It's a database of genotypes and phenotypes based on the phenotyping variables. It's funded by NHLBI, and Lucilla is the PI, and most of the work is done by the UCSD research team, including Dr. King, Dr. Doan, and the others. I helped a little bit on this project as a consultant. So this is a screenshot about the current search interface at NCBI about dbGaP, okay? So up to last year, November, there are about like 411 studies, top-level studies. But look at how many phenotype variables defined in those studies. It's like 140,000 different phenotype variables. So if you use the current search engine at the NCBI, for example, this slide is showing you enter the keyword for a variable called white. And maybe the intention is trying to search race, like Caucasian people, but the results actually will return all those things contain the word white, like white cell count or white potatoes. I don't know. It's more about probably a nutrition study or diet study. So you see that currently the search engine is mostly like keyword based. So our task is really how we can improve this, use more advanced NLP methods. And the first step is we really manually analyze all those phenotyping variables. trying to see how we can standardize this kind of description. And for example, we had defined one way to differentiate those variables, categorize those variables called topic, like a gender, smoking, and we will map. That's the main thing of the phenotype variable. But then we also notice sometimes when you describe a variable, it's not about the patient. It's about maybe the relative of the patient. So also I have to identify the subject of the information. And then we also realize we actually need a little bit higher level of category of those variables, maybe those about demographics. So by analyzing this, we come up with that kind of standard definitions of different each phenotyping. And next step is building a sort of NLP-enabled tools to map each phenotype variable to its standard representation. And this is a pipeline about a typical NLP engine, including like normalization. So we find all the abbreviations, we find all the variants, normalize it. Then we run NLP engine like a MetaMap. I don't know if you guys are familiar with that. It generates like a unified medical language codes. And there's other component on the line. So by doing that, we map the variable to the final representation. And this is a kind of early evaluation about accuracy is not that high yet. And the UCSD team also built a search interface to, once you index all the variables with the NLP engine, then you build the interface actually trying to search against that indexing. And this is the interface called PhenoDisc. So the other project I'm going to talk a little bit about is a new supplement project led by Dr. Hongfang Liu at the Mayo Clinic, Sergey at Minnesota, and myself. It's use an elastic search approach. Elastic search is like state-of-art indexing algorithm for big data. So it's actually is a distributed system, and it supports real-time indexing and query. And we also built an NLP system called NLP Tab, which have a visualized interface and to show the output from multiple NLP systems. So one system may be not good enough, but we combine all different NLP systems to boost the power of indexing. And this is just one diagram showing how we combine the Elasticsearch and the NLP tab together to actually search the biomedical literature. Another project I want to mention is the semantic-based search, which is also will be a funded supplement project led by Dr. Trevor Cohen. And the semantic vector is a relatively new distributed approach for representing meanings in a free text. It's more robust, scalable, and allows incremental indexing and better inference. So basically, we're thinking about apply this technology to find similar data sets. So the plan is quite simple. So we try to represent the data set with a semantic vector. Then we try to calculate similarity between two data sets by calculating similarity between two semantic vectors. So basically, that's another project we're going to start. Pretty much, I think my time's up, and I'm done with it. Thank you.
Thank you.
Okay, Kari, you want to get your slides up? So our last speaker is Kari Stephens from the University of Washington. She's a practicing clinical psychologist and biomedical informaticist. Oh. And she's a faculty member in psychiatry and behavioral sciences and biomedical informatics and medical education at the University of Washington.
And I don't use a Mac.
No.
Okay,
There you go.
thank you. So I'm for the biologists in the room what's called a hybrid vigor in data science. So I started my first career as an IT professional building data systems, the very first web-based medical record, deep data sharing kind of experience with institutional repositories. And then I went back and trained in becoming a clinical psychologist to be a clinician researcher as well. So as this hybrid vigor that I am, one of the things I've been doing in the last several years is immersing myself in the academic science of biomedical informatics. Doing that through our CTSA at the University of Washington, which is called the Institute of Translational Health Sciences. And one of the things that the ITHS has wanted us to be focusing on is a project called DataQuest, which is really about doing data sharing in our region across primary care clinics. So it was really fun to hear the primary care clinician talk earlier today, and talk about what it's like on the ground in these clinics and how do we leverage the data that they're collecting there for research in really important ways. So I want to share with you what we've done in DataQuest as another example of how we make data accessible, how we help researchers actually come to the data and not just use the data, but actually to partner with our community clinics as well, because it really needs to be a bi-directional relationship that often is seen as just a unidirectional relationship, and you see this helicopter research and the mistrust issues kind of explode. So, DataQuest is this data query extraction, standardization, translation project where we're doing data sharing across, in our region, which is considered to be these 5 states, the WWAMI region we call it, so Washington, Wyoming, Alaska, Montana, and Idaho, which our claim to fame is 25% of the U.S. landmass. So it's a big area, lots of different clinics, lots of different communities, cultures, governments within the states, et cetera. So what we've done is we created an initial pilot where we pulled together 5 different organizations, really, which now has expanded to over 15 different clinics that we have data connected in our region. Part of this is including many of the family medicine residency clinics across the institution, or I should say across our region, that are affiliated with our family medicine residency program. And we've also included the Critical Access Hospital Network, which is a network of RHCs, or rural health clinics, that serve very, very low population areas with very few resources. We also are very tied in with the Dartnet Institute, which is a national network of similar kinds of what we call practice-based research networks across the country that are also all data connected. So we see this in the ITHS as our sort of seed of data sharing that also is connected nationally with many other CTSA-based to some degree and some not CTSA-based data sharing networks as well, so that our researchers can access not only the rich data set that we have, but then can go much beyond that if they want to increase their denominators. So I wanted to talk to you a little bit about, let me just check here. So we have 2 different networks that we're partnering with. The first is what we call the WWAMI Region Practice and Research Network, which is the WPRN. And that one is a little more self-explanatory here. You can see who these different clinics are that we partner with. The kinds of trust with these partners is very easy, but also sensitive to make sure that they feel like they own the data. And I'll talk a little bit about the infrastructure we put together that's federated to protect privacy and build that trust with them. The other network that we work with is the Native American Clinical Research Network, where we've been trying to pioneer having clinics that are serving primarily tribal populations in the region also partner with us. So we've had some really nice relationship building successes there, but getting the data connected has been very difficult with Indian Health Services for any of you who might have that experience. Even with the tribes who actually own the data within their own practicing clinics on the reservations, we've still run into issues with IHS literally not giving us the password onto the system. So it's been difficult, but we have been able to partner more successfully with an Urban Indian Health Institute, which is very exciting. And the hope is that we can do that on a more national level, not just with our regional Urban Indian Health Clinic. So our model is federated, and the idea here is, in this graphic, is to give you guys a sense that we've got these blue cylinders on the left where ITHS has gone out and funded federated data repositories at the clinic, so they live behind the firewall. What we're doing is trying to, in technical terms, semantically align the data, basically put things in the same buckets across the different clinics so that when we want to go and query data across these, we can do it quickly and cheaply and easily. We also have affiliated organizations that are providing their own data repositories that also align with the same model that we have in place. And then we're in these reddish buckets, we've got nationally aligned partner organizations, primarily through the Dartnet Institute as well, and then folks that are not aligned. And the idea here is to be able to pull all these together into individual studies as needed. So where we're moving in the future is to actually adopt the OMOP model, which I know PScanner is doing, and I'm excited to hear tomorrow about how that's going with the CDRN effort. So just to give you an example of the kinds of research projects we've done within DataQuest, they really are varied, from various different topic areas like chronic kidney disease, behavioral health, service utilization within the clinics. We have a great partnership with the Northwest Pharmacogenomic Research Network, where we're trying to look at how we can use these data to help basic scientists who are trying to do discovery of pharmacogenomic directions to go in from the phenotyping data we have in these situations. But I think one of the issues, I'm just going to jump to this piece of it, one of the big issues we have in doing these kinds of research projects is addressing what researchers always ask us first about when we say we've got this data sharing network. And many of you can probably relate to this. And they say, so what data do you have in your system? And we say, well, how much time do you have to try to explain that? So we need a tool to do this. And what I did was squeeze into our DataQuest project in the last few years building a prototype of a data profiling tool. And in the last year or so, what we've done is propose that to the ITHS as one of our CTSA impact projects. So now we actually have a formalized project to build what I'm calling Find It, which is our new data profiling tool. So I want to tell you a little bit about that because it gives you a sense of how do researchers actually start to access our data. The idea behind Find It is really not about a cohort finding tool. There are lots of folks doing that kind of thing, I2B2, PopMedNet. There are lots of groups out there that are working on good EHR, electronic health record-based data sharing cohort finding tools. What I'm interested in is trying to profile what data in a simple way is in our system so that researchers can have a creative sandbox as they're formulating their ideas to go and look at what kind of data do you have so that I can think through as a researcher, would that be able to answer the question I have? And if not, how would I want to change my question based on the kind of data quality you have in your system? All right, so within this tool, right now we're about to launch Find It 1.0 in the next month. And we've got 3 different functions. And again, give me a little leniency here because this is what we came up with on a shoestring budget to kind of shoehorn in a prototype. So we took our best guess of what are the kinds of functions that we could put together quickly in a web-based tool. The first was to be able to browse the data by different types to get a sense to some degree of the depth and breadth. So what kinds of data are in the different types of fields you have that are more specific to what are the actual values held in the system. The right-hand column is the traditional data dictionary. What are your columns and rows that are in your data set? And then the middle column here is being able to dynamically put in any kind of ICD-9 code you want to get a count of how many patient lives are in the system. So as you do this, the idea here is that the user can interact and start to get menus of options. If they were to click, for example, patient demographics, over on the left, you'd see a pop-up, and they can look at gender, race, ethnicity, or language, get another pop-up, and you can't quite see the numbers, but the idea here is they can see a live count right there in our system of how many patient lives are captured, broken down by age for those different categories, with a percentage in there that gives you a sense of what denominator that lives with. And then the same, essentially in the middle here, where you can get a count of how many people have the particular ICD-9 code that you're interested in, as well as putting together a nice common list of sort of the top 10 most common issues you find treated in primary care. The data dictionary is pretty self-explanatory. You go in, you look up fields, columns, tables, and fields, and an English description. What I'm most excited about is moving to 2.0, right? We're going to launch 1.0, and I'm going, yeah. Anyway, let's do 2.0. Let's actually do this right. One of the things we're doing here, and here's our design team we've got here. This is a diverse group of folks. We've got biomedical informaticists, of course, but we've got clinicians, family medicine, physicians. We've got biostatisticians on this group. We've got students and postdocs. I've even got somebody who's got a communication PhD who's working with us through our eScience Institute. And it's just a really fun, a bioethics guy group where we all sit together in our design studio and use human-centered design methods to figure out what do researchers actually need in a tool like this. And our first step is doing a needs assessment. So we've been running qualitative study recently where I can share just very, very briefly some of the preliminary results from those interviews where we're asking researchers, what do you do now to get at secondary data sets? What do you go to? How do you find out about them? What do you like about that process? What don't you like about that process? What makes it easy? What makes it hard? Using that to then help inform us of what kind of functions do we need our new tool 2.0 to actually do. and then user test that as we go, and then track over time, does that actually increase from a marketing perspective the use of the DataQuest network? And I think that's a problem. I'm showing me my time's up, but if I can just finish.
That's fine.
Okay, so this was our needs assessment study. I think one thing I want to just point out really quickly here is the kinds of things that come up in needs assessment studies are things you never expect, but need to kind of get articulated, like the fact that researchers need to be able to trust the data. And how we do that now, it was almost universal in all the people we interviewed. They ask somebody. It was some mentor. It was some colleague. We need to figure out how to replicate that in these online tools we do. Data visualizations are another huge area that we're focusing in. So I just want to show you a little bit about that, where we're starting to work on looking at variations in codes across clinics and looking at statistical ways to actually do that. And then I'm going to skip through a little bit to the end here to give you a sense of also being able to dynamically interact. And I can't do it in the slide here, but in our actual demo, we're using a platform called D3 to do data visualizations, where if you mouse over these various bars, you can actually dynamically get a different set of bar charts over here on the right, so that you can see where the different variations are occurring of racial breakdowns and age breakdowns, et cetera. We're doing the same for disease categories and ICD-9 codes, and I just want to thank that we have a giant team. Others have done a better job articulating who all those folks are, but please know there's lots of people behind me working on this with me. So thanks.
Right on time, but we have time for a question or two if anyone has a question or comment. So one thing I've noticed, again, being in a field that's completely different, but listening to these talks, is that there are some things about making data searchable that I think are interesting and that I saw sort of recapitulated here. One, in many ways, this is again coming from our perspective, Google kind of put the bar very high for user interfaces. Everybody figures that you should have an interface that's so easy to use that you don't actually have to read any instructions. And yet, data are very complicated things, and more often than not, there's not an answer residing in their data. There's a set of data that you might be able to get to if you knew what was there, so that you could answer a question. So you're not answering your question directly, you're finding things that will help you answer a question. So the idea of this sort of facets and this ability to look at the data space is very, very important, and that generally happens from doing a fairly high-level query first with a general set of things, and then being able to sort of narrow down. The other thing is the ability to be able to combine tools, because everybody likes to think with structured data, you just need to be able to look at these value pairs. But in fact, there's a whole lot of interesting information in free text inside of all of these databases. And that if you just go strictly on a keyword in a sort of a search, you end up with a lot of false positives. You have to be able to interpret what is being said inside of those free fields. And so I really do think that this challenge of figuring out how to build a data discovery index, or how you would make the collective output of biomedical research searchable, is addressable, but I think it is going to take some time, because I think searching for data is different than searching for documents.
So let me just say that we feel that we're now in the position where our search engine is so sophisticated that we have to educate the users how to do it. We actually ran a test where we described one of the data sets, and then we had some graduate students see if they could find it. And it was very discouraging, because only about half of them found it. And what we had done was we had posed a question, and we said, suppose that you want to answer this question. How do you find the data set that will answer it? And it turned out that the best way to find it was to cut and paste the question right into the search box. And if you did that, you went straight to the data set. And people are so used to putting in keywords that nobody thought about doing that. So now we're trying to, we've actually been adding text and saying, well, here are 4 different ways to search that you might be thinking in different ways. You might be thinking about an author, or you might be thinking about a question, or you might be looking for a variable. And if you have this way of if this is what your goal is, there's a different way of searching, and they all work in the same box. So it it's, as you said, it's a difficult problem, right? How to get match the searching to the people.
Yes, I think so. And how much training they're willing to go through. Because if you have one thing, you can afford a lot of the. If you actually look across those 1,000 databases, there's 1,000 user interfaces that you have to master, 1,000 user interface that you need to figure out. And too often the answer that we will get from NIH or anyone else is, well, you need to send people to a 2-week training course. So that works great if that's the only database that you're ever going to need to use, but the chances are it's not. And so to send everybody to a 2-week training course for every single database is simply not practical. So in the idea of data discovery, it's exposing the data, making sure that the semantics are there, because that's another really critical piece, which you hear often echoed. But also, again, figuring out what that magic interface is and what are the strategies that you use. We've become much better at searching for Google documents. I heard it before that you don't go into Google and search for PRISM. You put PRISM and then some other qualifying word. That may or may not work in the data world. It may end up just giving you a 0 result. And so you do need to understand the strategies.
I was going to add to that for electronic health record data in particular. I think we also have a cultural struggle where folks for many, many years, many years in the last decade, when they know that these rich data sets exist now with EHRs coming onto the market, electronic health record systems coming onto the market, they can't get the data out. It's too expensive. It takes too long. There's this cultural barrier, I think, that we have among many of the medical researchers who also aren't technically savvy, who are therefore relying on strictly word of mouth. So trying to convince them that even if it's an easy searchable tool to use it is really difficult. So I think we have that challenge is, we're going to need probably something with a lot of credibility to get some popularity out there so that people start trusting that as a resource that they can go to.
Yes. Okay, I think that our time is up, but thank you very much, panelists.
Thank you.
Thank you for your attention.